Okay, here we go with the second video in our acid-base equilibrium notes. On this one, we're going to talk a little bit more about bases and figuring out the base dissociation constant, which is basically the same as the acid dissociation constant. And we'll talk about some factors and trends in acidity in different types of molecules. So weak bases react with water to produce hydroxide ions, just like the weak acids do. And similarly, they have the same equilibrium expression. We've got your conjugate base, your base, and similarly, you've got your base, your conjugate base, and your conjugate acid. So Kb is the base dissociation constant. We can use Kb to find concentration of OH, just like you could with Ka and H+, but once we know concentration of OH, we can figure out the pH, which is useful. So the pH of basic solutions. What is the pH of a 0.15 molar solution of NH3? So that's ammonia. That's a common weak base. That's something you should be familiar with. So NH3 plus H2O yields NH4 plus and OH minus. So our our base dissociation constant, Kb, concentration of NH4 plus, OH minus, in our initial base is 1.8 times 10 to the minus 5. So let's tabulate our data. So initially we have 0.15, 0 of the other stuff, and at equilibrium we know we have basically some unknown amount of the other two of our conjugates, and our initial acid is still basically 0.15 because, like we saw before, very, very small Kb, so not a lot of dissociation going on. So we can just plug those in. 1.8 times 10 to the minus 5 is x squared over 0.15. Solve for x. 1.6 times 10 to the minus 3 equals x. So that then is a little bit different. That's our concentration of OH, right? So our concentration of OH is 1.6 times 10 to the minus 3. So our POH is a negative log of that, so it's 2.8. The question asks us to find the pH. The pH is 14 minus 2.8, right? pH is POH, is Kw minus POH. So pH is 14 minus 2.8, so our pH is 11.2, which makes sense because we're talking about a basic solution, so you want it to be greater than 7. Another cool thing is Ka and Kb are related in that their product is Kw. So if you know one of them, you can figure out the other. So calculate Kb for the fluoride ion if Ka for hydrofluoric acid is 6.8 times 10 to the minus 4. I'll go ahead and pause. You guys can work on that and then come back to the video when you're set. Okay, so hopefully that was relatively simple. Kb is just Kw over Ka, so therefore Kb is 1.5 times 10 to the minus 11. So how do these things react with water? So reaction of anions, so negative ions with water. So remember, anything that's an anion is a base because it can be a proton acceptor. So they can react with water in a hydrolysis reaction to form OH minus and then their conjugate acid. Right? So you've got your base plus your water, your conjugate acid, and your conjugate base. Cations, very similarly, if they have an acidic proton, so something like NH4 plus, will lower the pH of a solution, like you'd expect. Most metal cations that are hydrated in a solution will also lower the pH of the water. So if you're thinking about something like this guy here, a big old cation 3 plus, because you've got this oxygen and lots of other oxygens, you're going to increase the polarity of this guy. It's going to draw these electrons even further this way, which makes it even easier for this water to strip away one of these hydrogens. That's why it's more readily available to drop out a hydrogen ion and create your H3O plus. So again, yeah, attraction between those non-bonding electrons in the metal causes a shift. Let me start over with that. So things that have an acidic proton, like NH4 plus, will lower the pH of the solution. Most things that are metals, most metal cations that are hydrated will lower the pH of the solution. Why is that? Well, you've got an attraction between all those non-bonding electrons on oxygen. So you've got all these oxygens here that causes a shift in electron density. So it pulls the electrons closer this way, makes it even more of a polar molecule, which makes it easier, makes this bond even more polar. It makes it easier for a water to come along and just pluck off one of these hydrogens to make your H3O plus and then lower this down to a 2 plus. So in general, the greater the charge and the smaller size makes a cation more acidic. So if you look at things like this, like Fe2 plus, Fe3 plus, greater charge is much more acidic, right? Aluminum, same charge as this guy, but it's more acidic. So some rules that you can apply to figure out what's going to happen to pHs. So an anion that is the conjugate base of a strong acid will not affect the pH, right? That's what we talked about. Like if you're thinking of like hydrochloric acid, the anion is Cl minus. That's not really doing squat to the pH because you're giving up so much hydrogen that's affecting the pH that way. The chlorine ion is not doing anything. So you can look for those conjugate bases of strong acids to really just to rule those out. Anion that is a conjugate base of a weak acid will increase the pH, right? Because then it's acting as a base, and it's actually a decent base, so it can increase the pH. A cation that is the conjugate acid of a weak base will decrease the pH. Right, so then you're making the cation as a positive, so it's likely to be a proton donor, which is going to decrease the pH. Makes sense. Cations of the strong Arrhenius bases will not affect the pH, basically the same as the first rule. Similar, like they're going to be totally dissociated. And other metal ions will cause a decrease in pH. So if you see a metal ion, generally it's going to be an acidic solution. And then if you have both a weak acid and a weak base, you have to look at the Ka and the Kb values to really be the tiebreaker. So if Kb is greater than Ka for the cation, it's going to be basic. If Kb for the anion is greater than Ka for the cation, it's acidic. And Kb, if they're relatively equal, it's going to be basically neutral. So let's try a couple of these. Determine whether aqueous solutions of each of these salts are acidic, basic, or neutral. So this guy here, what do you think about this one? If you look at it, hopefully, maybe this is starting to look a little bit familiar to you. Maybe it looks like acetic acid, and that's basically what that is, except we've got barium over here instead. And so when this dissociates in water, what are you going to get? You're going to get this CH3COO minus ion, acetate ion, which is a conjugate base of a weak acid, and then you've got barium, right? And that guy is going to be the conjugate of a strong acid. And so, strong base. So therefore, you've got this guy here, which is going to be a pretty decent base. So this is going to make a solution that is going to be greater than 7, a basic solution. Look down here, NH4Cl. When this dissociates, what are you going to have? NH4 plus and Cl minus. Cl minus is the conjugate base of a strong acid, so this doesn't do diddly squat, and then you're going to have NH4 plus, conjugate acid of a weak base. So that's going to be donating some protons, so that's going to lower the pH. CH3NH3Br. So this one might be a little bit unfamiliar to you, but this is actually, well, once you dissociate, you're going to get CH3NH3 plus. And that's actually the conjugate acid of a weak base, right? It's an amine group. And so therefore, it's going to be acidic, right? And then Br is going to be the conjugate base of a strong acid, hydrobromic acid. So that's not really going to do anything to the pH. So therefore, you're going to end up with a pH of less than 7. KNO3. What's going on with this? Well, when this dissociates, you're going to get a K plus ion and an NO3 minus ion. The NO3 minus ion is going to be the conjugate base of a strong acid, so that's not really going to do anything. And the K ion would be like the conjugate acid of a strong base. So those are basically not going to do anything. So you're going to be roughly a neutral pH. Al and ClO4, 3 of them. Oops, little typo here. This should be a lowercase l. What are you going to get here? You're going to get Al3 plus and then ClO4 minus. Al3 plus, metal ions, right? Those are going to be acidic. So that's going to be lowering the pH. And then ClO4 ion is a conjugate base of a strong acid, HClO4. So that's not going to be doing anything. So this is going to be making an acidic solution. So you can see how these different things would behave, and again, think about that equilibrium that we talked about in the first video and how they change pHs. So some general trends: the more polar the bond with your acid, or the weaker the bond, the more acidic it's going to be. And so basically acidity is going to increase from left to right and across the row, and then from top to bottom down a group. So if you're thinking about what your periodic table looks like, HF is a weak acid. This guy is a very strong acid, right? This is a very hydrogen, very electronegative. It's going to hold on to that guy. This is a relatively large molecule. It's going to be easy to pop those H's off. Something like an oxyacid, so these are things that have an OH group on them. They're bonded to some other atom or atoms, in this case Y. As you increase electronegativity of the Y, the more acidic it is. So this might be weird at first. You might be saying to yourself, well, there's an OH, wouldn't that be a base? Well, not really in this case, because again, you're bound to that Y. And so as this guy increases electronegativity, again, we're going to be pulling that electron density from the hydrogen closer this way. It's making it even more polar. And so again, it's easier for this water to come along and pluck the hydrogen off and get your H3O+. Same idea with oxyacids. These are things that have different numbers of oxygens. So as you increase the oxygen, you're also going to be increasing basically the overall polarity of that bond. And so it's going to be easier to get rid of these guys, and these guys actually then become strong acids even. So 4 oxygens, 3 oxygens, those are strong acids. So the more oxygens you have, the stronger your acidity, stronger your acid. And then finally, resonance in the conjugate bases of these carboxylic acids. This is a carboxyl group, a C double bonded to an O, single bonded to an O, stabilizes the base. So because you have resonance, this the negative charge has more places to go and makes it basically less of a base. So this makes this whole solution more acidic as well. So example, let's arrange these guys in order of increasing acid strength. So I'm going to let you guys pause and think about this for a sec, and then come back to the video when you're ready. Okay, hopefully you came up with something good. So in increasing acid strength, so who's the weakest here? So we can look at polarity, okay? Potassium has a very low electronegativity, so KH is probably the weakest. Hydrogen has a 2.1, arsenic has a 2.0, bromine 2.8, and selenium has a 2.4. So you can just base it entirely on that way. So since Br is the most polar, it's going to be holding those electrons most closely, and this is going to be most likely to dissociate. That makes that the strongest acid. Lewis acids, just like the Lewis structure, when you think of drawing your compounds, these are anything that can be electron pair acceptors. Lewis acids are electron pair acceptors. So something that has an empty valence orbital can be a Lewis acid, and then bases are things that can be electron pair donors. So anything that could be a Bl base is also going to be a Lewis base. And Lewis bases can interact with things other than protons, though. So for example, phosphorus acid has this Lewis dot structure over here. So think about this. Y is H3PO3 diprotic and not triprotic. So there's 3 hydrogens, but why isn't it considered a triprotic acid? Well, think about polarity. The pH bond is not really all that polar, right? So pretty similar EN values. But the OH bond is very polar. So those guys are going to be the ions that are going to be more acidic. These guys are going to be ones that are more likely to drop off that OH. This is going to be holding on to it a little bit more closely. So that's why it tends to only give up 2 hydrogens. So a 25 ml sample of H3PO4 is titrated with 0.102 molar sodium hydroxide, and that requires 23.3 mils of NaOH to reach neutralization. What is the molarity of this H3PO3 solution? I'm going to let you guys pause and work on this, because this is a good one to practice and sort of sum everything up. So go ahead and pause and see if you can make some progress with this. Okay, hopefully you're coming back to me with a great answer on your paper somewhere. So what are we going to do with this one? All right, here's our equation. All right, we've got our H3PO4 and our NaOH. All right, we have our concentrations. So we have our volumes and our molarities. So we know how many moles of NaOH we have. And so once we know how many moles of NaOH we have, we can figure out how many moles of H3PO3 we have. That's a typo. That should be H3PO3. And so therefore, we can figure out our concentration because we know how many moles we have, we know how many liters we have. So we have 0.46 molar H3PO3. What do we do with that now? Okay. The solution, all right, so that's figuring out that one. What's the molarity of H3PO3? Next question, building on that. The solution from part B has a pH of 1.59. Calculate the percent ionization and the Ka1 for H3PO3. So how do we figure that out? Okay, well, you know how to do this. The concentration of H plus is just the antilog of the pH. So it's 0.26 molar. So now we can create a table. So you have your initial concentration. We have how much it changed. We have our final concentrations. Plug that in, and we get our percent. Well, we can get our final concentration. We get our percent ionization, 55%. And so then we can plug those in and get our Ka, 0.31. And that is the end of our acid-base equilibrium unit.